We're going to take a look at graphing some piecewise functions and evaluating the domain, and that should say and range of these guys. This video is going to be especially helpful because it's going to show a variety of different types of functions, so quadratic, absolute value, square root, and how we can kind of graph those guys. So I highly suggest just kind of doing a basic table of values for a lot of these that you're unfamiliar with. It'll be very helpful. So let's get started with our first example. Okay. So this piecewise function has just two different parts to it. So our first part is where x is less than 2. So 2x plus 1 will only show up for values to the left of 2 there, and we'll have an open circle on the end at the right. And the absolute value of x divided by 2 is going to be everything starting at 2 and then going off to the right. So let's start graphing this first function. So this is a simple linear function. So it's just a line, has a y-intercept of 1 and a slope of positive 2. So I'm going to go ahead and use that. Now, my second point that I'm going to be putting right here, because we are strictly less than 2, and this is the value of 2 right here, I'm going to make sure that that is very clearly an open circle, right? Because we butt up against 2, but we do not actually ever equal 2, all right? So anything below 2 is that line there. All right, let's graph our second function here. So this is an absolute value. When you're doing this, because this absolute value would normally start here at our origin, because we're not adding or subtracting anything, you can always start graphing there and then just erase. So if you want to go ahead and do that, you can. So because we're dividing by 2, we'd be at 0, then 1/2, then 2, then 2.5, then 3. And you'd say, okay, well, this is what kind of the right-hand side of this function would look like, but I'm really only interested in starting it at 2. So I'm going to erase up to there and go ahead and make sure that that's a really closed circle because that's where we're starting. Alternatively, you could just, plug in some points here, right? So we're going to start at 2, and I'm going to say, all right, well, absolute value of 2 divided by 2 is just 1. Right? Absolute value of 3 divided by 2 is about 1.5. They're exactly 1.5. Absolute value of 4 divided by 2, that's 2. And then I have a nice way to start my graph. So we know that this is going to look approximately like a V, and we knew that this first one would be a line with a positive slope. All right, so let's talk about our domain and range for this guy. Okay, so our domain, our x values, we start off here at -infinity, then we continue along. We kind of hit a bump right here at 2 where we don't have a value, but it's picked up immediately at 2 by this absolute value function, and we continue off towards positive infinity. So we have all real numbers in our domain here. So our domain is from -infinity to infinity. And we want to figure out, is our range doing the same thing? So we start down here, right, and we continue all the way up. So we're at -infinity down here, continuing up. But then we can kind of hop over to this graph, right? So they start overlapping right here, and this continues off to positive infinity. So we have no gaps in our range either. So we're from -infinity to infinity. Okay, so that was our first example. And we're going to keep doing a couple more. So stick around for as many examples as you need. Okay, second example. So we have 3 functions this time. First function, this is just the function, right, y equals 4. So that's going to be our horizontal line, and we're doing that for x values strictly less than -3. So that means at -3, we're going to have an open circle here, And then for all values less than -3, our output value is going to be 4. So it's just this nice horizontal line here. Okay. Okay, so let's see what's going on for this absolute value. Okay, so this is an absolute value that is shifted down 4 units. So absolute values normally start at the origin. This guy has been shifted down and will start here at 4. It's really nice that we have that in our domain of this function because it makes graphing it real easy. So when we're graphing an absolute value function that's not stretched or compressed at all, we can just kind of take an increase, kind of either up 1 right, up 1 left each time. And we're going between -3 and +1. So I'm going to go up and left until I get to -3, and that was a less than or equal to sign, so we do have a closed circle, so we can connect that. And then go ahead and do the right, and that is a less than or equal to 1. But then we need to stop because that is where the domain for that function stops. Okay, now we have our square root function. Okay, so what are we doing with this guy and this? Oops, I actually miswrote that. I wanted that to be a +2 in there. Okay, so if we were graphing this square root function normally, this +2 would tell us we moved the start of our square root function to the left 2, but we don't actually want to start there because that is not within our domain. We want to start here at 1. What's the value when x is 1? So we're going to go ahead and just approximate that. So we're just going to sketch this function and then erase, or you could use a table of values as well. So we know we want this to look a little like a curve like that. So shortcut for graphing these, you start at kind of your beginning point, and then we can go up 1 over 1 squared, back to your beginning point, up 2 over 2 squared, so that's over 4. And then, continue that pattern. So if we go up 3, we go over 3 squared, which we don't really need that much. The only problem with this is we do kind of need an approximate value for what is this function at 1. So that would be about the square root of 3, which is approximately 1.7. So I'm going to go right here at 1 and stick that 1.7 right in there. Now, when I go to connect this graph, I'm going to ignore everything to the right of 1. And I am going to go in here and make sure that that point that I'm going to put at 1 is an open circle, because if we reference our domain, there's not an equal to there. So we're non-inclusive at that point. So we're going to go ahead and sketch that function. And I'm going to get rid of everything to the left of 1. So that was all kind of what we might consider side work. We don't want to leave that on your graph. So if you're graphing it that way, do erase that, because I don't really want to see that. Okay, so this one gets a little bit more interesting. So domain is not terribly interesting here. So we pick up, let's see, where's my marker? So domain, we're off here at -infinity. We continue along this red line, this horizontal line. When we hit -3, we automatically jump to having a value here on the blue line. We continue along, we have a value there. We jump up to this green line, we continue off to infinity. So at no time did we have a gap at any point. Okay, range. So this is a little bit different. So we want to start with how low did we go. So our range, our bottommost point there is at -4, right? And then we want to take a look at what happens as we go along. So we go from -4, and then we kind of go up here to -1. And then we were right here. So this is -4, -1. Then we were on the green line. That was our root 3. And the green line, even though it doesn't look like it, this green line is going to continue increasing off to infinity. So remember those square roots, even though they look like they taper off, they really don't. So we do have a gap here. So all of this that I'm writing just, shouldn't really be on your graph. It's just a tool that you can use to help with your range. So we do have a bracket because we do include -4, and we go to -1. And again, that's a bracket because we have that solid point there. And when we go for our second part after our gap, we want a parenthesis because we have an open circle there at √3. And then we continue off to infinity. We do not need to worry really about this red line because this red line is just the value y = 4, which is included here in this second half of our domain. So 4 is somewhere in between, well, not in between, but, well, yes, in between the square root of 3 and infinity. So we don't need to add that in there. All right, next one. Okay, let's graph this. So again, 3 different graphs. We're going to start with a squared function. So this is where x is less than or equal to -2. So this +3 tells me I'm moving to the left 3. So that is going to be the vertex. We're looking for a parabola here. Okay. So when we're graphing our parabola, you might remember, your shorthand. So we go over 1, up 1, and we do that in both directions, right? And then if we go over 2, we would have to go, right, over 2, we go up 2 squared. So it's kind of similar to that root that we did before. So we would end up there at 4. I'm not going to bother doing that off to the right because that's outside of the allowable domain for this part of our piecewise function anyway. I'm going to make sure this looks like a curve and not like an absolute value. So I don't want a distinctive point there. I just want a curve. And that's our nice little partial quadratic. Okay, second part. This is a line with a slope of +1. So we're going between -2 non-inclusive, so no equal sign there, and 4 inclusive, we have an equal sign. So for this line, we start at a y-intercept of -1, and then we have a positive slope of 1. So once I get here at my leftmost point, I'm going to make it an open circle because we didn't have an equals, and I'm going to continue this trend until a x value of 4. Okay. And we are going to make sure that that is a closed circle because we did have an equal to sign there at 4. Okay. Last function. So this guy is a touch on the odd side. It's a 4th degree, but really it's just going to look kind of like a fat parabola here. Okay, so if you're uncomfortable with this guy, just table of values it. It becomes pretty apparent what this guy is doing. So rules about shifting are the same. So this -5 in here tells me that the vertex of this function is going to be starting at 5. And then we could just do a quick table of values, right? So we have x, we have y. So we know we want to see what it's doing at 4 because that is sort of its tail end that we have to graph. And then we'll just get a couple others, say at 6 and 7, right? So this is the nice easy peasy way of graphing this guy. So 4 minus 5, that's -1. -1 to the 4th is just going to be 1. 6 minus 5, that's 1. And then 1 to the 4th, that's just 1, right? And then 7 minus 5, that's 2. 2 to the 4th is 16. So you can see this guy gets real big real quick. But we know we got 1 and 1, and then we know 7 is going to be like way up here. So we're going to go ahead and give this guy a really steep ascension, right? So fat parabola may be a bad description. It's kind of the bottom part that gets a little on the flat side, but then it does get kind of skinny. It's a bit weird. Okay, so that's that guy. So let's go ahead and do our domain and range. So domain, again, we don't have any gaps, right? We're going off to negative infinity, off to positive infinity. We pick right back up again, and we pick right back up again here, right? So no gaps. Ooh, one thing I did do wrong was this needs to be an open circle because we didn't have an equal to sign. Okay, so domain is just negative infinity to infinity. Okay, range is where we get more interesting. So range starts down here at -3. And then we keep continuing up. So we keep going up, up, up. We haven't had any gaps yet. And we can see these functions are going to continue on forever. So we're going to have an inclusive value there at -3 and go off to, oops, not a bracket. There we go, infinity. Okay, one more example. If you are done, the next one isn't terribly interesting, but we do touch on a bit of a weird root function. So stick around if you need to, otherwise go off, do your practice. Okay, last one. I'll try to make it a quick one. Unfortunately, these problems do tend to take, maybe around 5 minutes. Okay, so first up, we have a quadratic. So we're anticipating a parabola. This guy, we're going for less than or equal to -2. Well, it starts at -2, so we're kind of chopping off the entire right-hand side of this parabola. So over 1, up 1 squared, over 2, up 2 squared, and we got our nice left side of a parabola. And we do want a closed circle because we did have that equal sign. Okay. Next one, root. Okay, so what's going on with this that I forgot to write in here? Nothing. Everything's fine. Okay, so our root function looks kind of like that, and we're only going between -2 and 4. All right. So for this one, I'm just going to go ahead and stick in the end values. So if I go ahead and put -2 in there, well, that comes up with a bit of a problem, doesn't it? So if I do -1 plus the square root of -2, you can't tell me, but maybe say aloud to yourself, what's the issue there? Well, this is the issue. We can't take the root of a negative number. That function actually doesn't exist there. So in this domain here, -2 to 4, we can't actually graph any of this function from -2 until we hit 0, right? It doesn't quite exist. So we want to start by plugging in an x value of 0, and we're just going to have a gap. So that's going to affect our domain maybe. All right, so at 0, square root of 0 is 0, then kind of plus that -1. We're down here at -1. Now I'm going to put an open circle there, right? Or no, closed circle, sorry, because that is included in our domain, right? 0 is between -2 and 4, so we're good there. And then I'm just going to go ahead and do the end. So just go ahead and stick 4 in there. Square root of 4 is 2. 2 plus -1 is 1. All right, so we're going to be right here, and then that is going to be an open circle since we don't have an equal sign, right? And then because we know our root functions, they curve kind of like that in the upwards direction, unless we have a negative going on somewhere. We can go ahead and just connect these with a curve. If you wanted to find your x-intercept, where y is 0, that would be at 1. That could help you create a nicer curve there because we are going to have that x-intercept in this range. Okay, so that was kind of the weird one on this guy. Last one, x is, or y is equal to -6, right? So when we look at this, we kind of think y is equal to -6. That's what we're graphing. So this is just going to be a horizontal line, but it's only going to exist for x values greater than or equal to 4. So I'm going to go down here to -6, and where x is 4, put a solid line, and it's just going to be horizontal and off to the right. Okay, so we've got the three pieces of our function, so let's go ahead and deal with our domain and our range. Okay, domain. We were off to negative infinity there. We're off to positive infinity over to the right. We're okay here at 4 because we have an open circle and the blue function, but a closed circle and the green function. But we do have a gap. This is the first time we've seen a gap in our domain here. Okay, so when we go to write this, we go from negative infinity and then to 2, and that was inclusive because we had a closed circle. Then we got to do a hop. So union with the second part of our domain, which started at 0, we had that closed circle, and then went off to positive infinity. Okay, how about our range? So our range starts by just having a single value here at 6, right? And then we have a gap, and then we go from -1, and then we go up. Our blue function ends, but luckily our red function continues on. We don't really care which function it is as long as one of them exists. So our range here, we have a single value, -6, which we can just write as a -6 in brackets, union that second half where we started at -1 and then went off to infinity, and that -1 should be in a bracket because it is a closed circle. Okay, so if you need some more help, the math program, Delta math program, that has some really good explanations. You're going to be doing a few of those, or hop into office hours.